Hi, we're from the TRILOW-G team, and the work we're about to show you is going to be flying in space in less than a year. In fact, we're the first UCSB capstone team ever to go to space. Not only that, but in the time that our project is up there, it's going to be testing a technology that could change how we will explore the Moon and Mars. You see, as we explore beyond Earth, there are countless challenges that we encounter. One of these is anchoring and securing things to the surfaces of these bodies. Much like on Earth when we build a foundation for a house, structures in space need to be held to the surface. These could be smaller scientific instruments, places for astronauts to live and work, or even larger structures like radio telescopes.
But, like a lot of things in space, this problem turns out to be really challenging. Heavy foundations like those on Earth would be prohibitively expensive to launch into space. An anchoring device that's placed into the ground is appealing, but then placing them becomes difficult. Simply pushing the device into the surface is hard. If you've ever pounded a stake into the ground, you felt the problem. As you go deeper, you rapidly need more and more force. And in space, this is even worse. Gravity on Mars is only 1/3 of that on Earth, and on the Moon, it's only 1/6. That means that a 180-pound person would only be able to push down with 30 pounds of force on the Moon.
But there's a solution, and to understand it, we need to take a quick detour to soft robotics. Everyone's seen robots like these, big, heavy, and rigid robots that are great at performing predictable tasks. But if we bent our idea of what a robot could be, we could come up with devices like these. By being soft and deforming easily, soft robots like these can solve problems that traditional ones can't. One type of soft robot in particular can help us with our anchoring problem. Inspired by vines and plant roots, the Hawks lab here on campus has pioneered a new type of tip-extending soft robot. Powered by compressed air, these robots are able to grow and lengthen their tip without their outer surfaces moving at all. This solves a couple of the problems we had with placing an anchor earlier. Instead of sliding through the soil, the walls of the anchor stay in the same place, even as the anchor grows deeper, reducing the force you need at the surface to place it. With the right design and conditions, these soft robots can even self-anchor, taking no external force to grow arbitrarily deep. This technology has other applications as well. If a robot could burrow deep under the surface, scientists could collect data that they otherwise wouldn't have access to.
But all the tests of these robots that have been performed have been on Earth, in terrestrial soils. That's where we come in. We're sending a payload to space on a Blue Origin rocket that will test these soft robots in conditions that mimic those on the Moon. This will include a gravitational environment and a soil medium like that on the Moon. Let's talk about how this is going to work. Before launch, our payload will be mounted into a payload locker in the crew capsule of a Blue Origin New Shepard vehicle. After this, the vehicle will launch from Blue Origin's facility in Texas and take the capsule containing our experiment up to an altitude of 250,000 feet. Then, the capsule will separate from the propulsion module and will spin up to rotate once every 5 seconds. Just like how you feel pushed to the side when you take a turn in a car, our payload will feel a force because it's rotating around the center of the capsule. The rotation of the capsule will be carefully controlled such that this force will be equivalent to that it would feel from gravity on the Moon. Once the capsule gets up to speed, our payload will have only 2 minutes to complete its tests. Because of the vibration, shock, and acceleration of launch, the soil contained in our payload may be compacted in an unrealistic way. Therefore, the bed of soil will be prepared by both vibrating it and allowing pressurized air to flow through it. Once the soil has been prepared, the actual testing can start. First, a soft robot anchor is tested by simultaneously increasing its internal pressure and letting material move through its center, allowing growth at the tip. While this happens, the force felt to hold the base of the robot stationary is measured. Once the tip of the robot reaches its desired depth, the whole robot will be pulled up to measure how much force it can withstand without coming free. Finally, the robot will be retracted back into its housing, ready for the next trial. After the trial completes, a hole will be left into the soil, which would hurt the accuracy of subsequent trials. Therefore, the preparation process used at the start of the test is repeated.
Now, a test of just a soft robot is useful, but being able to compare it to a rigid device called a penetrometer is even better. Including one gives us a measurement of the soil we're testing with and its preparation, and another anchor-like device to compare our soft robot to. To this end, the next trial that is performed is with the penetrometer. Much like the soft robot test, the penetrometer is pushed into the soil bed to a specified depth and pulled out, all while force and position are being measured. Each of these 2 tests is repeated a total of 3 times, with the soil being prepared before each. After these 6 trials, the 2-minute lunar gravity period will be nearly complete. As the capsule falls back down to the ground, its rotation will be slowed. Finally, at about 3,000 feet above the ground, parachutes will be deployed and slow the descent of the capsule until it falls back to Earth, landing nearby where it launched. From this test, we expect to collect data which shows not only that a soft robot anchor would be easier to place than a rigid one, but that they would be able to withstand more force when pulled up. The data we collect will also help engineers understand how the tests we can run easily here on Earth will compare to the real behavior of such devices in space. If these anchors work as we expect, they could enable new methods of moving around, building, and gathering data on the surfaces of bodies in the solar system and beyond. Thanks for listening. We'd love to tell you more about our project. When you take your next trip to the moon, think about our technology and how we helped put down roots on the moon.